Hello, everyone. Today, we're going to look at a very interesting topic. It's almost like becoming a fortune teller for chemical reactions. A way to predict their future using mathematics.
Have you ever wondered, when a doctor gives you a medicine and says, take this every 6 hours, how do they know that? Is it just a guess? Well, no. Behind that simple instruction, there's some very powerful chemistry at play. And today, we'll see exactly how chemistry provides a precise answer to this question.
So this special tool that helps us answer these how-long questions, we call it integrated rate equations. That's the topic for today. Its whole job, its entire purpose, is to let us predict what will happen over the timeline of a reaction.
Okay, now for your exams. This is the main definition you should know. A simple rate law, you see, only tells you how fast a reaction is right now. But an integrated rate equation, that's much more powerful. It gives you the full story. It lets you calculate the concentration of a reactant at any point in time. Now, to make this idea really clear, let's forget about chemistry for a minute. Let's think about something much simpler, something you've probably seen at home.
So just imagine a bathtub with the drain open. A regular rate law is like looking at the water flowing out and saying, okay, at this exact moment, the water is draining at, say, 5 liters per minute. See? It's just a snapshot in time. It's only telling you the speed right now.
But the integrated rate equation, that's completely different. It's like having a magic formula that can tell you, okay, if we start with a full tub, then in 8 minutes the water level will be exactly half, and in 16 minutes it will be almost empty. It's not just a snapshot, you see, it's the full movie of the bathtub draining.
So let's connect the parts of this analogy. The water level in the tub, that's like our reactant concentration. The size of the drain, that's our rate constant, K. But here is the most important part. Think about it. As the water level goes down, the pressure also goes down, right? So the water starts draining more and more slowly. This is exactly what happens in a chemical reaction. As the concentration of reactants drops, the reaction rate also slows down.
So the big question is, how do we get this amazing predictive power? How do we go from the rate right now to predicting the future? Well, we use mathematics. Specifically integration, to change that simple rate law into a formula that can handle this slowing down over time. Let's look at this a little closer.
This comparison here makes it so clear. A rate law is just like your car's speedometer. It only tells you your speed at this one instant. But an integrated rate equation, that's like a GPS. It knows your speed, but it also calculates the whole journey and predicts what time you'll arrive. One is a snapshot, the other is the entire trip.
Let's try to picture this in our minds. Imagine you have a beaker filled with a dark blue dye. Now, you add a chemical that makes it react and lose its color. What will you see? At the very beginning, when it's dark blue, the color will fade very fast. But as it gets lighter and lighter, the change becomes slower and slower. Why? Because there are fewer and fewer dye molecules left to react. The integrated rate equation is the perfect mathematical formula to describe this exact process of fading.
All right, now let's talk about the most important and I would say life-saving application of this entire topic, and that is the concept of half-life.
And here we are, back to our first question about medicines. You see, the way our body breaks down a medicine is a perfect example of something we call first-order kinetics. Now that just means the speed of the breakdown depends only on the concentration of one thing, the medicine itself. And this whole process is described perfectly by an integrated rate equation.
Let's walk through an example. Suppose you take a 500 milligram tablet, and let's say the half-life of this medicine is 6 hours. What does that mean? It means after exactly 6 hours, half of the medicine is gone. So only 250 milligrams will be left in your body. Now, what happens after another 6 hours? Half of the remaining amount is gone. So half of 250, that's 125 milligrams left. You see the pattern? Every 6 hours, the amount is cut in half. That fixed time period, that is the half-life.
And this is where we come to a very surprising but very important fact. For these first-order reactions, the half-life is constant. It does not matter what the starting amount is. Just think about that. Whether a patient takes 1,000 milligram dose or a 500 milligram dose, the time it takes for that amount to become half will be exactly the same. It's an amazing property, and it depends only on the rate constant K. So, let's just quickly recap the main points. First, integrated rate equations are the tools we use to predict a reactant's concentration at any time. Second, the easiest way to think about it is using the draining bathtub analogy, And third, the most powerful application is calculating the half-life of medicines, which tells doctors how often you need to take a dose.
Really, if you just remember these 3 things, what it is, the bathtub analogy, and the medicine example, this topic will feel much, much lighter for you during your exam preparation. I promise.
So, I will leave you with one final question to think about. We've talked a lot about medicine, but this tool is so powerful. What about other things? The decay of radioactive elements, for example, or even how quickly food goes bad in your fridge, or how pollutants break down in the environment. Now that you have this tool to predict the future, what other processes do you think you could model with it?